diode second approximation. So under this approximation, this time we will now consider what is known as the barrier potential of the diode. So it is not just we consider the diode as a switch, but rather we also consider the barrier potential of the diode. So if it is silicon, we consider the 0.7 volts. If it is germanium, we consider the barrier potential of 0.3 volts. So as you can see on the diode curve, the voltage, as long as the voltage reaches the barrier potential of 0.7 volts, that is the only time that there will be a current that will flow through the junction of your diode. So meaning to say, when the diode receives a forward voltage of 0.7 volts, that's the time that there will be a flow of current across the diode, or that is the time that there will be a flow of current in a circuit. On the other way around, under the reverse region, obviously, there is no diode current because we see the diode as an open switch with the barrier potential. So even if there is a barrier potential, as long as it is under the reverse bias, the diode is like an open switch. So there is no current that flows through it. So the diode current is simply equal to 0. But then, there is the value of our reverse voltage. Okay? The reverse voltage has a value. It has a negative value here. Why? It's because, say for instance, we will apply here a reverse bias. Okay? And so that is negative and this is positive. So we treat now the diode under the second approximation as an open switch and consider the barrier potential. Okay? So if you're going to place now a tester across this, what the tester is actually seeing is actually the voltage across it. So what the tester is actually seeing now is actually the terminal of the reverse voltage applied, which is the negative VD. And that's the reason why we have the voltage VD here. And there is no current since under reverse bias, the diode is treated as an open switch. So let's apply now this concept with this example. So we are given the same diode, which is silicon, the same load, which is 1000 ohms, and a supply voltage of 10 volts. Now, what is being asked here is for us to compute for the load voltage, the load current, and the diode power. So please be reminded that the power diode, or the power dissipated by the diode is simply equal to power dissipated of the diode is simply equal to what? It is simply equal to the voltage across the diode, okay, multiplied by the current that flows through the diode. Okay, so that is the formula. Or better, I'll just write this one in a better way. So I have here voltage of the diode across the diode, multiplied with the current that passes through the diode. So my apology for this. I'm just using a person. Okay, so let's start. So let's first check the diode. What type of bias does the diode have? So if this is the anode, which is positive, okay, and it is connected with the positive terminal of the supply voltage, and the cathode is connected with the ground, and the ground is connected with the negative. Therefore, we can now say that the diode is actually in a forward bias. Again, this time we are using the second approximation. So we treat the diode now as a closed switch. There, as a closed switch. And please do not forget the barrier potential of 0.7 volts. So there is a barrier potential of 0.7 volts. So this is now the equivalent circuit. If we are asked for the load voltage of the diode, so as you can see, if this is 0.7 volts, applying now KVL, okay, so you enter the, applying KVL, what do we have? applying KVL, we have negative 10 volts. We enter the negative 10 volts. We enter the positive 0.7 volts. Okay, the terminal is 0.7 volts. Okay, and then, okay, so if this is positive, negative. So obviously, the polarity here is positive, negative. So we enter here the positive VL. Okay, equated to 0. Because as you recall, KVL simply means the voltage across the loop is simply equal to 0, or the sum of the voltages in a loop is simply equal to 0. Therefore, VL is simply equal to 10 minus 0.7, or that will simply give you a value of 9.3 volts. So, that is now the voltage of the load under the second approximation, considering the barrier potential of the diode. Next, question is, what is the load current? So obviously, VL, okay, is simply equal to IL multiplied with the load. Okay, so we already have the VL. The VL is simply equal to 9.3 and our load is 1K. Therefore, our load current is 9.3 milliampere. And then lastly, power across the diode is simply equal to what? The voltage across the diode, okay, multiplied with or power dissipated by the diode multiplied with the current that passes through the diode. Okay, so if you are only talking about the diode, where is the diode? So the diode is simply from this point. Please check this one. The diode is from this point up to this point. Okay, that is your equivalent of the diode. It is equivalent as a closed switch with the barrier potential. Okay, so if that will be the case, the voltage across this diode, across the series short, is simply equal to 0. But you still have the 0.7 volts, so that's the reason why you have the 0.7 volts here. And the current that flows throughout the circuit in a series connection, because the diode is in series with the load. Okay, so the current is simply equal to 9.3 milliampere. Having now the power dissipated across our diode, which is simply equal to 6.51 milliwatt. So that is now how we computed for the diode current and how we computed for the power dissipated by the diode. Using the second approximation, aside from the closed switch, we consider now the barrier potential. Thank you.